Welcome back to the deep dive. Today we're tackling a problem that has, been a huge headache for large language models since day one.
The memory problem.
Exactly, the memory problem. You feed a model this massive document, ask it to find one little detail from the very beginning, and nothing. It's like it has amnesia for anything beyond a few pages.
Context length amnesia, yeah.
Well, we've just gone through some incredible new research from Sakana AI and the University of Oxford that proposes a surprisingly simple fix. They call it DroPE.
That's dropping the positional embeddings.
And their paper is fascinating. It explains not just how their fix works, but why all the previous attempts have been fundamentally on the wrong track.
So our mission today is pretty clear. First, understand why LLMs have these short fixed memory windows. And second, and this is the crucial part, figure out how DroPE pulls off what they call zero-shot context extension.
Zero shot, meaning it can handle longer stuff right out of the box.
Right, without the insane cost of retraining the model on super long documents. It's a huge deal for efficiency.
Okay, so let's get into the technical side. The big villain of this story is something called positional embeddings, right? PEs.
Specifically, rotary positional embeddings, or ROPE. Almost every big model uses them.
And we need them because transformers don't inherently understand that words come in a specific order.
Exactly. ROPE gives the model a sense of direction. But here's the catch. If you give the model a sequence that's longer than what it saw during training, those directional clues go haywire. They become out of distribution.
And the model's performance just...
It degrades and fast.
So, okay, if ROPE is the barrier, the obvious engineering fix is to try and, stretch it. We've seen a bunch of these. PI, ROPE, NTK, and YaRN is a really popular one.
All these so-called ROPE scaling methods, yeah.
But the paper argues they don't really solve the core problem. So why not? I mean, models scaled with YaRN, they still sound very coherent.
And that is the critical distinction. You're right. They are very good at one thing, which is maintaining low perplexity.
Which basically means the model isn't surprised by the next word. It sounds good. It's fluent.
Perfectly fluent. But that fluency is an illusion. It's hiding a much deeper failure.
So we're saying the smooth talk is actually a lie. The model is coherent, but it's blind to information that's far away.
Precisely. This is observation 2 in the paper. These models consistently fail at retrieval tasks, especially in what they call a needle in a haystack test.
Right, where you hide one key fact, the needle, deep inside a huge document of irrelevant text.
Exactly. You stick it, say, 8,000 tokens in. When you test a model like YaRN, its ability to find that needle is, well, it's pretty much the same as if you had just cut off the document at its original training length.
So it's not even looking past that original boundary, it's just ignoring it.
It's ignoring everything beyond its comfort zone, even while its output sounds perfectly fine.
That is pretty depressing. So we've been fooled by surface-level coherence. But why? Why does stretching the positional signal cause this deep semantic failure? It feels like it should help.
It's a really subtle technical point, but it's the core of the issue. To make ROPE work for longer sequences, these scaling methods have to compress the signal, specifically the low frequencies of the ROPE rotation.
Okay, what does compressing low frequencies mean in, plain English?
Think of it this way. The high frequencies in ROPE help the model with local stuff, grammar, what word comes right next. But the low frequencies, they're for the long-range relationships. They power the model's semantic attention heads.
The parts that actually understand meaning and context across the whole document.
Exactly. So when you aggressively compress those low frequencies to make things fit, you're essentially jamming that long-range radar. The model literally loses its ability to connect a token at the beginning with a related token way at the end. The semantic matching just collapses.
I see. So that explains the failure, but it also creates this big paradox.
Yeah.
If ROPE is the bottleneck,
Hmm.
why do we even use it in the first place? Why can't we just build a model without it?
And that is observation 1. We use it because it's incredibly important for efficient training. PEs provide what's called an inductive bias. It's a head start that helps the model learn way, way faster.
So a model trained without PEs, which the paper calls a no PE architecture, it just learns much slower.
Much slower. And it's not just a little worse, it's visibly worse. The no PE models have worse perplexity throughout the entire training run. Without those explicit positional clues, the model struggles to figure out which words are important. That non-uniformity in attention develops too slowly.
The paper has a great example for this. Let's say you give a no PE model the simplest possible sequence, just A, What does the model see?
Well, without an explicit position marker, it has no mathematical reason to believe the first A is any different from the fifth A. All the attention scores are identical.
So it can't learn anything about order from that step.
And worse, the gradient, the actual learning signal for position, just vanishes. It goes to zero. DroPE completely sidesteps that problem by giving the model a pre-built structure for position right from the start.
So DroPE is like scaffolding. You put it up to build the structure quickly and correctly.
That's the perfect analogy.
Which brings us to observation 3, which is really the whole insight of DroPE. The scaffolding is temporary.
Precisely. It's a training accelerant. The massive discovery here is that once the model has learned how to handle position with the help of DroPE, you can actually take the DroPE away. The model has internalized the knowledge.
And it doesn't forget how to handle sequences.
It doesn't. The capability is baked in. And removing the DroPE after pre-training is what unlocks that long context generalization.
So the magic is all in the timing. Use PEs to learn fast, then throw them out before they can cause problems at inference. Let's walk through the DroPE method itself.
It's almost shockingly simple.
3 steps.
That's it. Step 1. You pre-train your LLM just like normal, using standard DroPE to get that fast convergence.
Okay, nothing new there. Then what?
Step 2. You drop them. You completely remove the DroPE mechanism from every single layer of the transformer.
Just gone. Okay, so what's the catch? That's step 3, right? There has to be some expensive fine-tuning.
Not at all. That's the beauty of it. Step 3 is just a very short recalibration phase. You just continue pre-training for a little bit longer at the original short context length.
Wait, at the short context length, you're not even showing it long documents.
Nope, you don't need to. The goal isn't to teach it long context. It's just to let the model's weight settle and adjust to the fact that the explicit DroPE signal is now gone.
And is this recalibration phase a heavy lift, computationally?
It's incredibly light. The paper does mention using something called QPay norm for really big models, but that's mostly just to keep training stable and let them use a slightly higher learning rate. The core idea works without it. It's just a quick adjustment period.
Okay, let's pivot to the results, because this is what everyone listening really wants to know. Does this simple, fast, 3-step trick actually beat all the complicated scalable methods?
Empirically, it's not even close. The performance gap is huge. DroPE delivers zero-shot generalization that just blows the competitors out of the water. It proves the model can actually use information from deep inside a sequence.
So let's bring back the needle in a haystack test where we said YaRN and the others basically failed.
The difference is night and day. In tests where the sequence length is, say, 8 times longer than the original training context, DroPE significantly outperforms YaRN, RopeNTK, and even other alternatives like Alibi. It actually finds the needle.
Wow. And what about on more complex real-world tasks? The paper mentions long bench results.
Yes, and this is maybe even more impressive. They applied DroPE to their small M base model. On the long bench suite, which has really hard tasks like question answering across multiple documents, summarizing government reports, DroPE improved the base model's average score by over 10 times.
10 times.
10 times. It shows a massive practical advantage in long context comprehension.
That is an incredible jump. And it comes without the massive cost. We have to talk about the efficiency here because the numbers are just kind of stunning. How small is that recalibration cost?
It's minuscule. So the small M360M model was trained on 600 billion tokens originally. To get over 95% of its original performance back after dropping DroPE, they only needed to recalibrate on less than 5 billion tokens.
So less than 1% of the original training budget.
It's 0.8% to be exact. It's a rounding error.
Think about that. You're unlocking true long context capability for less than 1% of the initial compute cost.
Yeah.
That could save literally billions of dollars across the industry.
And it scales. They did the same thing with the much larger Llama 2.7b model.
Yep.
That was trained on 4 trillion tokens. The DroPE recalibration only took 20 billion tokens. That's 0.5%, 0.5%.
Just 0.5% of the budget.
Yeah.
And it still outperformed the other scaling methods. Okay, but one last check. You're performing major surgery on the model. You're ripping out its positional embeddings. Does that damage its original short context abilities? Does it lose any of its core intelligence?
That's a great question, and the answer is no. The data is very clear on this. The in-context capabilities are fully preserved. When they tested the DroPE models on standard benchmarks like HelloSwag or PIQA, they performed just as well as the original base models, sometimes even slightly better.
So you lose nothing. and you gain massive context extension.
You lose nothing.
So when we boil this all down, the big aha moment here is that we have to completely rethink what positional embeddings are. They're not a permanent fundamental feature of the architecture.
They're a scaffold, a temporary tool.
A scaffold you use to build a house,
Yeah.
and then you're supposed to take it down.
Exactly. It's absolutely essential to get the training done quickly, but then it actually becomes a liability for inference. It gets in the way. You have to drop it to unlock the model's true long context potential.
This really does feel like a new standard for building these models, tackling one of the biggest challenges with, such an elegant and low-cost solution.
And it teaches us a really powerful lesson, I think, that some of these canonical trade-offs we assume in AI, like you have to sacrifice long context for fast training, maybe they aren't real trade-offs at all. Maybe they can just be solved by using different architectures at different stages of the pipeline.
Training versus inference.
Right. And this brings me to a final thought, something for you to chew on. Now that we know that PEs can be treated as a temporary training tool, what other parts of our AI models, what other fundamental components might actually just be scaffolds? What else should we be dropping once the core learning is done?